Thanks. Thanks, first of all, to the organizers for putting together this wonderful conference and for the invitation. Can you, just in the back, confirm that you can hear with the microphone? Okay. So I see a slight misprint that was meant to be algebras in field theory and gravity, but gauge theory will do. So quantum mechanics textbooks usually envisage a quantum system probed from the outside by an observer who is looking at the system but isn't part of it. As observers in the universe, we're in a different situation. We're part of the system that we're trying to observe. Moreover, we can't resolve the quantum microstate of the universe, and that's not only because of technological limitations, but also because we cannot see beyond the cosmological horizon. So some of standard textbook quantum mechanics doesn't quite apply. I'm going to assume that a few ingredients of standard textbook quantum mechanics are valid. So first of all, I'll assume that observables form an algebra A, meaning a vector space. You can add or multiply observables. You can multiply an observable by a complex number, and they have an associative multiplication law, like operators on Hilbert space. I'll assume that there's a notion of Hermitian conjugation of observables, and I assume what we measure are expectations of observables in the state of the universe, however that state of the universe is to be understood. And I assume one more thing, which is that positive observables have positive expectation values, meaning that if I denote the expectation of an observable A with this symbol with the brackets, then the expectation value of A dagger A is non-negative for all A. That's actually enough to imply that our observations can be described by a Hilbert space, although it wouldn't be necessarily a Hilbert space that describes the whole universe. We just formally introduce a symbol psi equals psi1 that represents the presumed state of the universe. And then for any observable A, we introduce a symbol psi sub A that represents A times psi. It represents the state of the universe after acting with A. Then inner products are defined by saying that the inner product of psi A with psi B, I hope most of you can see the green dot, is the expectation value of A dagger B for any two observables A and B. Now, because of the positivity assumption on the last slide, this definition is consistent with all the properties that Hilbert space inner products are supposed to have. So we actually get a Hilbert space after we divide by null vectors and possibly take a completion, because Hilbert spaces are supposed to be, in a certain sense, complete. Now, that doesn't mean that H describes the quantum state of the universe. It does describe all measurements we can make, but it was constructed with no knowledge of what was beyond the horizon, if there is a horizon. So it will give us no information about what's beyond the horizon. It's not a Hilbert space for the whole universe, but it is a Hilbert space for us. Since we can see distant galaxies, the action of our algebra A on H contains information about distant galaxies, but it doesn't contain any information about what's beyond the horizon. Even from a complete knowledge of how the algebra A acts on the Hilbert space, which is highly idealized compared to what we can actually learn from experiment, we will learn nothing about what's beyond the horizon. So there is a sense in which it might make sense to talk about entanglement wedges of gravitating regions, such as the region of space-time that we on planet Earth are living in. But some knowledge of what's beyond the horizon is needed to predict an entanglement wedge beyond the horizon. Well, what kind of algebra is the algebra of observables accessible to us? To get a simple answer, we need two steps. First, to get a simple answer, we have to assume that what we measure are bounded operators. A mathematical reason for this assumption is that bounded operators can be multiplied. So if our observables are bounded operators, they do in fact form an algebra. By contrast, it's problematical to multiply unbounded operators in general. But there's a physical reason for considering bounded operators, which is that in practice, even if we measure something that in theory is unbounded, like the electric field, we only measure it in a certain range. So in practice, our measurements do seem to be measuring, for example, in that example, a bounded function of the electric field. So Although this discussion is an idealization, it seems that assuming what we measure are bounded operators is reasonable physically, as well as a tremendous simplification mathematically. There's one more step needed to get a simple structure theorem for A, and this is roughly, we do not try to distinguish operators that can't be distinguished by experiments. More precisely, consider a sequence of observables A1, A2, and so on, with the property that for all states psi chi, the matrix elements of A n between those states has a large n limit. If so, then we define an operator A whose matrix elements are given by those limits, and we say that A is the limit of that sequence, and we consider A, this limit, to be part of our algebra. Mathematically, this is called a weak limit. Physically, the logic is that an experiment measures finitely many matrix elements with finite precision. So under the hypothesis I stated, no experiment will distinguish A sub n from A if n is sufficiently large. So for experimental purposes, A is in fact the large n limit of A sub n. Finally, physically, it's well motivated, at least in a closed universe, to assume that the center of the algebra consists only of complex scalars. In an open universe, if the observable region goes off to spatial infinity, there might be gauge charges that would make us modify the statement, but I'll assume today that the center consists only of complex scalars, as we would expect in a closed universe, for example. Given A and B, the algebra is what's called a von Neumann algebra, and C makes it a factor, the analog for algebras, of a simple as opposed to a semi-simple Lie group. So such von Neumann factors have a simple, roughly speaking, a simple threefold classification, which is as follows. First of all, if A has no useful simplification beyond the axioms, then that's an algebra that's said to be of type 3. So with the type 3 algebra, you can do quantum mechanics because I incorporated enough axioms so that quantum mechanical probability, interpreting measurements in terms of expectation values of algebra elements makes sense. So a type 3 algebra gives us enough to do quantum mechanics and no more. There actually are theorems showing that out of all von Neumann algebras, a generic one is a type 3. So one version of this statement is in this paper. So that's natural. It says that if we're given the axioms A, B, and C, nothing useful follows beyond that. We can do quantum mechanics and that's it. There are two kinds of simplifying properties the algebra might have, in which case it's said to be of type 2 or type 1. A type 2 algebra has a trace but no irreducible representation. A type 1 algebra has an irreducible representation. So those are the two important special cases of algebras that have useful properties beyond the axioms. By a trace, we mean a complex valued linear function on the algebra, which I'll denote as trace A, that obeys two properties. The trace of AB is the trace of BA, and the trace of A dagger A is non-negative for all A. The trace doesn't have to be defined for all elements of the algebra, only for a sufficiently large, dense set. For a type 2 algebra, the function trace is not a trace in a Hilbert space representation of the algebra. A type 2, any von Neumann algebra has Hilbert space representations, as I explained at the beginning, but a type 2 algebra, the trace in a Hilbert space representation of a type 2 algebra is infinite. The function that I call the trace is a sort of renormalized version of a Hilbert space trace with an infinite factor divided out. An algebra of type 1 has an irreducible representation in a Hilbert space H prime. This H prime is not necessarily the H that we constructed at the beginning in an abstract way to incorporate observations. We defined at the beginning Hilbert space and we completed to get a von Neumann algebra, and that algebra might be of type 1, and if so, it'll have an irreducible representation H prime, which will not be the one we constructed by the general procedure. Then von Neumann showed that A is actually the algebra B of H prime of all bounded operators on H prime. And then there's a natural trace, just the Hilbert space trace in the Hilbert space H prime. It's not defined in all elements of the algebra, assuming H prime is infinite dimensional, the trace of the identity is plus infinity. But it's defined on a dense set of, well, on a large subalgebra of operators said to be of trace class. For either type 1 or type 2, once there's a trace, we can define density matrices. If H is any Hilbert space representation, which could be the minimal one that we described earlier at the beginning in an abstract way, or maybe a bigger Hilbert space that includes degrees of freedom beyond the horizon. So at the beginning, I described a Hilbert space that was sufficient for our observations, but someone else who did somehow have access to the whole universe maybe would have used a bigger Hilbert space to describe the whole universe. But in any case, given any Hilbert space representation, a density matrix is an operator in the algebra that obeys the usual condition of a density matrix, except that now trace, what I'm calling trace, is not a Hilbert space trace. It's this, in the type 2 case, it's this more abstract trace function. It's not hard to prove for both type 1 and type 2 that such a density matrix always exists. It's a positive operator that, roughly speaking, is an element of A. There's some fine print. And it has the standard normalization condition of a density matrix. If psi is a unit vector, then the trace of the density matrix is 1. So the density matrix, just as in ordinary quantum mechanics, will be a positive element of the algebra with trace 1. Once we have density matrices, we can define von Neumann entropies or Rényi entropies and other functions considered in quantum information theory by standard formulas. Most of the definitions use only the axiom satisfied by the trace function, not the fact that it actually is a Hilbert space trace. However, there's an important difference between a type 2 algebra and a type 1 algebra. For a type 1 algebra, the trace is literally the trace in an irreducible representation. No renormalization is required, so the definition of the entropy is completely natural. For a type 2 algebra, there was an infinite renormalization in the definition of the trace. So this corresponds to an additive renormalization of the entropy. To check that, let's see that if the trace is multiplied by a scalar, then to satisfy the definition of a density matrix, we have to rescale the density matrix by the opposite factor. And the effect on the entropy is to shift the entropy by an additive constant, which is the same for all states. So the best we can say is that entropy in a type 2 algebra is defined up to an additive constant that's independent of the state. What are really well-defined are entropy differences. This is analogous to entropy in classical mechanics. In classical physics, entropy differences can be defined by integrating the first law. But there's no natural zero of entropy in classical physics and no natural way to fix an overall additive constant. Type 2 algebras have a further bifurcation into two subtypes, type 2-1 and type 2 infinity. In a type 2-1 algebra, the identity operator has finite trace, and the trace function can be normalized so that the trace of the identity is 1. And more generally, the trace is finite for every element of a type 2-1 algebra. In a type 2 infinity algebra, the trace of the identity is infinite, just as for a type 1 algebra with an infinite Hilbert space. And the trace is only finite for a subalgebra of trace class elements. Now, what do we expect the algebra of observables for a given observer to be? First in quantum field theory, and then possibly with gravity. Well, the interesting case is an observer who, because of black hole or cosmological horizons, cannot see the whole universe or even a complete Cauchy hypersurface. If you can see the whole universe, you'll have access ultimately to a type 1 algebra of the familiar situation with an irreducible representation. The interesting case is when you can't see the whole universe. For example, here's a Penrose diagram of an observer in de Sitter space. As usual for Penrose diagrams, time runs vertically. And I've chosen coordinates so that an observer propagating on a geodesic lives on the left edge of the diagram. The left edge is the world line of the observer. And then the causally accessible region is this green wedge, bounded by past and future horizons. So in such a situation, one will not get a type 1 algebra, certainly not in ordinary quantum field theory, and not in gravity to the extent that we actually know how to do computations. The time-like tube theorem of quantum field theory, which is a sort of precise version of HKLL reconstruction, says that the algebra of observables that the observer can measure, the algebra of operators along the observer's world line, is the same as the algebra of observables in the whole causal wedge shown in green. A heuristic explanation is that the observer can shine a laser beam at any object in the green region, and by seeing what is reflected back, can learn about what's there. So you can not just passively observe, you could passively observe something down here, but you can actively do experiments on something in the green wedge. And so it turns out in ordinary quantum field theory that the observables along the observer world line are the same as the observables in the green wedge. A classic result that goes back to Araki is that in quantum field theory, the algebra of such a proper subregion is of type 3. So the observer can do quantum mechanics, but can't describe those observations by density matrices or entropies, which are type 2 and type 1 concepts. The type 3 nature of the algebra has a dual in ADS CFT that was studied by Liu and Leutheuser a few years ago in work that's influenced a lot of subsequent developments. So here I've drawn schematically the Penrose diagram of an asymptotically ADS black hole. So it's a two-sided situation. There's a left asymptotically ADS region and a right region, and a spatial hypersurface connects the two. And if you live on either the left or the right, you see past and future black hole horizons. And for example, an observer with access to the right boundary, the solid blue, the associated causal wedge is the light blue region outside the past and future horizons. So the blue wedge, as I just said, is the region causally accessible to the right boundary, the dark blue, where we imagine the observer to be making measurements. In the approximation of treating the bulk theory as a quantum field theory in a fixed background, the algebra of the light blue region is of type 3, so in an appropriate limit, that's also the case for the algebra of observables on the right boundary. The appropriate limit is when you completely turn off gravity and treat the bulk theory as an ordinary quantum field theory in a curved background. So if the boundary dual theory is an SUN gauge theory of some integer n, so for a definite integer n, the thermofield double state. So the natural state in this universe is called the thermofield double state. For some fixed n, first of all, the thermofield double Hilbert space is just a tensor product, HL tensor HR, of two copies of the CFT Hilbert space. And then, for fixed n, the thermofield double state is simply a vector in this tensor product Hilbert space. And for fixed n, the algebra acting on either h left or h right is a type 1 algebra with h left or h right as the irreducible representation. So for fixed n, the algebra accessible to the observer on the right is just the type 1 algebra of all operators on h right. That's a simple answer, but it has a drawback. The drawback is that for finite n, for n a definite integer, notions of space-time and causal structure are not precisely defined. So although we have precise quantum mechanics with irreducible action on a Hilbert space, for when n is a finite integer, puzzles about causality and so on in the field of a black hole, or similarly in cosmology, are not expected to be sharp when n is a definite integer. If we want to do quantum mechanics in a world where semi-classical notions of causality are meaningful and sharply defined, we need to take a large n limit. And then it's no longer true that the thermofield double state is a state in a tensor product Hilbert space. It's a state in a, if you're above the Hawking-Page transition, the thermofield double state is a state in a new Hilbert space that you can define, the thermofield double Hilbert space. It's a Hilbert space that describes states of the quantum fields in a connected spacetime. In that large n context, the causal wedge of the boundary is this subregion shown here, And the algebra accessible to the boundary observer is of type 3, as it always is, for this quantum field theory case of a subregion of spacetime. So even though for finite n, the right boundary would have a type 1 algebra, in the large n limit, it should be possible to define an emergent type 3 algebra. To define this emergent algebra, Liu and Leutheuser considered single trace operators normalized with no overall factor of n. For finite n, they would generate the type 1 algebra of the boundary. In the large n limit, they have divergent expectation values. So to get operators with a large n limit, you have to subtract their expectation values, say at some inverse temperature beta, which you choose to be above the Hawking page transition. And then the subtracted operators do have large n limits. And ADS-CFT duality, together with what's known about quantum field theory, says that the algebra that they generate is of type 3. Since it's the same as the bulk algebra of the causal wedge, treated as an ordinary quantum field theory at g equals 0. So the boundary algebra defined, as I tried to summarize in the top of this slide, is supposed to be dual to the bulk algebra of the causal wedge at g equals 0. Now, an important detail is that this large n limit of single trace operators does not contain the Hamiltonian. Keeping track of powers of n, you'll see that it contains h over n, but not h itself. And the subtracted version of h over n in the large n limit becomes, I wrote a C number, but I should have written that it becomes central. So in the large n limit, the generator of time translations is not contained in the algebra. Time translations act as an outer automorphism of the algebra. So we'll come back to that outer automorphism in a few minutes. But for now, we just note, following Liu and Leutheuser, that it means that in the large n limit, the operators in a time band of the boundary are a proper subalgebra. In fact, the boundary interpretation of this subalgebra is that it's the algebra of a smaller bulk region. So here, if I take a time band of the boundary, which is this dark blue, this partial dark blue, well, part of the right boundary that's been written as dark blue, the causal wedge is this light blue subregion, and the algebra of the light blue subregion will be a type 3 subalgebra of the algebra of the whole causal wedge. Similarly, although I didn't make a picture, we could make a semi-infinite time band bounded in the past but not in the future, and that would again give a type 3 algebra. So various properties of the bulk geometry and dynamics are reflected in properties of these emergent bulk algebras. I'll just mention a couple of facts which you might hear more about later from some of the panelists, although unfortunately their time will be short. We've already seen the connectedness of the two sides of the thermofield double is reflected in the type 3 nature of an emergent boundary algebra. There's an analog which you might think of as quantum connectedness between a black hole that's been evaporating for a long time and the radiation it's emitted. You can also give a criterion for the existence of sharp horizons, even in the stringy case. That means even when g squared n is not taken to infinity. So we don't expect a sharp definition of the horizon for finite n, but it's not so clear a priori if the horizon is a sharp notion when general relativity is replaced by string theory. So you can argue from this type of setup that at least in certain cases you can have a precise notion of a horizon. With finite g squared n, that means non-zero g squared n, that means a stringy situation, but in the large n limit. And there's more which you perhaps will also hear of from Nima in his short talk later on algebras associated to time bands and stringy geometry and chaos and other things. Now, there's a slightly different story if we consider a slightly different large n limit in which we include the Hamiltonian. But before explaining that, I want to give some heuristic reasons to think that type 2 algebras might be related to gravity. So, well, here we should imagine semi-classical gravity, where I imagine semi-classical gravity means any situation in which semi-classical notions of causality make sense, possibly incorporated to a stringy realm where you have stringy horizons, as I just mentioned. but not a completely quantum mechanical situation with finite n. The basic reason you might think that type 2 algebras are relevant to gravity is that in gravity it seems that we can define entropies even when we cannot define quantum mechanical microstates. So we've been grappling with that ever since the early days of black hole thermodynamics. A quantum theory with entropies but no microstates is a good candidate to be described by a type 2 algebra. So that simple reason is perhaps the most basic reason you might think type 2 algebras are relevant to semi-classical gravity. Somewhat more specifically, we often compute in gravity things that we call traces, even though they aren't traces in any way we understand. So we compute things that we call trace e to the minus beta h by a gravitational path integral. For example, in ADS space, we take certain asymptotically ADS boundary conditions with a circle at infinity of circumference beta, and we say the path integral with that asymptopia calculates trace e to the minus beta h, but the topology is wrong for the function we're computing to be interpreted in terms of a sum over states in any way that we really concretely understand. But anyway, we compute what we call trace e to the minus beta h, even though it's not a trace of any operator in any Hilbert space. And we compute more complicated things that we also call traces. So even though we don't have a Hilbert space H and operators on that Hilbert space, such that the quantities we compute really are such traces. So we call these functions traces because they obey the abstract properties of traces, namely these two conditions, which were the axioms I stated earlier for a trace. They obey these conditions for any O and O prime for which these quantities are finite, such as something like this. Now, typically, we believe we are computing large N asymptotics, not limits, because these quantities usually don't have limits. But we usually think we're computing large N asymptotics of functions that really would be traces if N was a positive integer. But in the large N asymptotics, these things aren't really traces. We just call them traces. So one might suspect that these objects could be interpreted as elements of a type 2 algebra whose trace function is what we're computing. Now, an elementary example where you can make this very explicit is JT gravity coupled to matter in space-time dimension 2. So we compute from disk path integrals, for example, with the disk of circumference beta in example 1, or disk of with boundary segments of length beta 1, beta 2, and beta 3 separated by operator insertions, what we call operator insertions, but we aren't really inserting operators. We're inserting ingredients in a path integral. Anyway, we call the things we're computing traces even though there's no one-sided Hilbert space in which they are traces. Well, there's no Hilbert space at all in which they are traces. An interpretation is that objects such as e to the minus beta h and so on are elements of a type 2 infinity algebra in which the trace function is computed by a path integral on the disk. Well, what's this good for apart from hanging a plaque on the wall and saying that we've discovered a type 2 algebra? One answer is that although JT gravity does not have one-sided Hilbert space describing states of a single black hole, it does have a two-sided Hilbert space describing states of an entangled pair of black holes. And in this situation, you can define type 2 infinity algebras A right and A left for the left and right boundaries respectively. And you can show that they're each factors, they have trivial centers, and they're each other's commutants. That means A left consists of all operators that commutes with A right and vice versa. The statement that they are commutants means that even though classically there can be a long wormhole between the two sides with a lot of matter inside the wormhole, so I've drawn it schematically here. Now I've drawn a long wormhole between the two sides, a lot of massive particles in between, and the causal wedge of the left and right boundary is very small, and there's a lot of stuff that neither observer can see classically. However, the fact that the two algebras are commutants means that the tensor product is the algebra of all operators on Hilbert space with no gaps. There's nothing in between that's not accessible on left or right, or at least not accessible to an operator with if you have combined access to the left and the right. For example, the renormalized length between the two sides. is an operator in A left tensor A right in JT gravity with matter. This is a sort of non-perturbative version of entanglement wedge reconstruction. There's a gap between the two causal wedges, but there's no gap between, roughly speaking, the reconstructible wedge of the left or right, where by reconstructible wedge I mean whatever you can learn about by studying either A left or A right. There's also no known classical geometric description of these reconstructible wedges, except in the usual sort of semi-classical limit. And it would seem that only in the usual semi-classical limit should one hope for such a classical description of what these wedges mean. But algebraically, there's a sort of abstract entanglement wedge reconstruction in the large N limit using these type 2 algebras. This has an interesting variant in n equals 2 supersymmetric JT gravity. In the long wormhole situation, in bosonic JT gravity with any amount of matter in the bulk, the energies E left and E right measured on the left and right can be arbitrarily small, but they can't be strictly zero. However, in n equals 2 JT supergravity coupled to matter, no matter how much or what matter there is in the bulk, there exists exactly zero energy state, a completely supersymmetric state that looks like a supersymmetric ground state to an observer on either left or right. In other words, there can be an extremal black hole, as seen on either side, with any amount of matter behind the horizon. So there's a large space of two-sided extremal black holes, one for every SU1 1/1 primary field of the matter system. This is just the conformal supergroup of n equals 2 JT supergravity. If you take the type 2 infinity algebra that would exist in general and project it to the ground states, you get a type 2-1 algebra that acts on extremal black holes, as essentially suggested here and further studied in a recent paper. Now, in space-time dimension bigger than 2, in theories of ADS gravity with a known CFT dual, we expect that for positive integer n, there's a one-sided Hilbert space Hn, which at high enough energies is a black hole Hilbert space that we don't understand it very well. So, as I've said, we expect these things are really traces if n is a positive integer. The only trouble is that when n is a positive integer, we can't make the statement that the high energy states are black hole states very precise. Such notions that involve causality are tied to an asymptotic expansion near n equals infinity. As I've told you, near n equals infinity, we get answers we can't literally interpret as Hilbert space traces because the Hilbert space Hn does not have a large n limit. What we do have in an asymptotic expansion near n equals infinity is a description by a type 2 algebra. Presumably, the reason that limit is important is that it's the region where we can make contact with semi-classical ideas of causality, which are tied to conceptual questions about black holes and quantum cosmology. JT gravity is different and easier, more tractable for a couple reasons. One is that the analog of n is the number of C of matter fields, and no large C limit is needed in the analysis. And that's good, but then there's something which is bad, that even for fixed C, there's no one-sided Hilbert space. So for the analog of integer n, JT gravity is still in the type 2 situation because of the second fact. Above 2 dimensions, something somewhat similar to JT gravity, with the bottom-up theory of gravity potentially lacking in ultraviolet completion, like pure Einstein gravity, or Einstein gravity with electromagnetism, which potentially, if it lacks an ultraviolet completion, also lacks a well-defined black hole Hilbert space. But nevertheless, to the extent the theory makes sense, we can compute trace e to the minus beta h by Euclidean path integrals, and you could expect to give such results a type 2 interpretation to the extent that the theory makes sense, even if it isn't a truly well-defined theory with a true black hole Hilbert space. Another way to say the same thing is that if you have a continuous spectrum but a finite partition function, that's impossible in the type 1 world. It's impossible in the world we take for granted in ordinary quantum mechanics, where a continuous spectrum implies a divergent trace. But if it's perfectly possible to reconcile a continuous spectrum with a finite trace if the object whose trace you're taking is an element of a type 2 algebra, and by trace you really mean the trace of the type 2 algebra. So whenever you're tempted to think that you have a continuous spectrum and a finite trace, you probably have a type 2 algebra in your hands. Now, a more explicit construction of a type 2 algebra is available in a couple of important cases. One is a two-sided Schwarzschild black hole, and also an analog in quantum cosmology. So for a two-sided black hole, let H be the generator of time translations. So as you recall, the time translations go forward in time on the right boundary, but move backwards on the left boundary. The Hamiltonian H can be written as an integral over an initial value surface S, which I'll take to be at t equals 0, where t is Schwarzschild time. So the initial value surface is that horizontal surface. And we take the vector field V, the Killing vector field associated to time translations, and the stress tensor, and we integrate over S, and we get the generator of a symmetry of the two-sided black hole. In heuristic arguments, you often want to decompose S as a union of S right and S left of portions on the right and left of the horizon. And then you write H as H right minus H left, where H right and H left are the parts of this integral to the left or right of the horizon, where you usually include some minus signs to compensate for the fact that H, to make sure that H left as well as H right are moving forwards in time. Now, in ordinary quantum field theory, this decomposition is not correct. If you try to make it, you run into ultraviolet divergences. Trying to make this decomposition leads to ultraviolet divergences at the bifurcation surface, which is the common boundary of the two regions, S left and S right. However, in gravity, there's no problem with the decomposition H equals H right minus H left. In fact, this is just the ADM expression for the total conserved charge H in terms of ADM energies, H right and H left, measured on the right and left boundaries. So now, given this knowledge, let's try to define an algebra of observables accessible to an observer who lives in the region U right, to the right of the bifurcation surface. So, in ordinary quantum field theory, the algebra of observables would be a type 3 algebra A0. But in the presence of gravity, the full algebra of observables has one more generator, H right. So A is the von Neumann algebra generated by A naught together with H right. So this symbol just means the algebra generated by these things taken together. Well, H right is an observable for an observer in the right region, because it's just the ADM mass over here. But the corresponding energy H left commutes with all observables in the right region. And the observer on the right knows nothing about what H left is. So let's just give it an abstract name X to emphasize that we're taking the viewpoint of an observer who knows nothing about what H left means. Now, we can trivially write the formula that H is H right minus H left, or H right minus X, in the form H right is H plus X. So taking gravity into account, we can describe the observable algebra in region UR, to the right of the horizon. It's the algebra generated by A naught together with H plus X. So we took the naive quantum field theory algebra and we added one more observable. Here we've run into a classic construction of a type 2 algebra from a type 3 algebra. Takasaki and Kahn in those days were not trying to do quantum gravity, they were trying to understand type 3 algebras. Since type 3 algebras were hard to understand, it was useful to find a way to construct a type 2 algebra out of a type 3 algebra, and in a certain sense the construction can be inverted, though I won't explain that. So it gave information about the type 3 algebra, which a lot of the theory of type 3 algebras was based on. Anyway, the mathematical name is that what we get when we add H plus X to A0 is the cross product of the algebra A naught by the one-parameter symmetry group generated by H plus X. This construction could be defined for any H plus X where H generates an automorphism of the algebra. But in this particular case of time translations of the two-sided black hole, H is the generator of what's called the modular automorphism group of the thermofield double state, as interpreted by Sewell. And the initial algebra was of type 3, so then the cross product algebra is of type 2 infinity. That's basically the result exploited by Takasaki and Kahn, by coincidence, in what was also the early period of black hole thermodynamics. So if A naught acts on a Hilbert space H naught and H is an operator on H naught, then the cross product Hilbert space, cross product algebra acts on a Hilbert space which is the original Hilbert space tensored with L2 functions of x, which I'll just call L2 of x. So what Takasaki, and then exploited also by Kahn, did was to add, well, to make the Hilbert space a little bit bigger by including functions of one more observable, but an uninteresting observable in the sense that it commutes with everything. And then you add H plus X, where H is a symmetry generator, to the original algebra. And the theorem here is that that produces a type 2 algebra out of a type 3 algebra. And you could make this quite explicit. If psi TFD is the thermofield double state in the original Hilbert space, and psi hat is the thermofield double state times e to the x over 2, then the trace of any operator is its excitation value in the state psi hat. And it's, although I won't show a proof, it's not too long to prove that that does have the properties of a trace. This is a type 2 infinity algebra, not type 2-1, since the trace of the identity, by definition, is the excitation value of the identity in this state, which is the norm of the state. And I assume that the thermofield double state is a unit vector, but the x part of the inner product is this divergent integral. So the trace of the identity is infinite, so this is a type 2 infinity algebra. And physically, that's related to the fact that you could throw in mass and make the black hole heavier and heavier with more and more entropy. So indeed, since we have a trace, we can also define an entropy, and we can also compare this entropy to the usual generalized entropy. But when we do so, we have to remember that the generalized entropy is not defined for all states. It's defined for quantum fields in some state psi in an almost definite spacetime. It's not defined, I'll say what it is defined for. To get a definite spacetime here, we need the canonical conjugate of x, which is a relative time shift between left and right boundaries, to have an almost definite value. So the canonical conjugate of x is a parameter in the spacetime geometry, a time shift between the two boundaries. It needs to have an almost definite value. So a state in which it has an almost definite value is a state of the form psi tensored with f of x, where f of x is slowly varying. We could also more generally let psi depend slowly on x. Those are states for which the usual generalized entropy formula makes sense. And you can show that the density matrix, in this paper we computed the density matrix approximately and showed that for this kind of state, the entropy defined in the type 2 algebra agrees with usual generalized entropy up to an important state-dependent constant, which from this point of view was not defined. Subsequently, the exact density matrix was computed for such states without assuming f is slowly varying. In general, it's hard to use this to compute entropy when f of x is not slowly varying, because it's hard to compute the logarithm of the density matrix. But a highly non-semiclassical limit where x rather than its conjugate is sharply peaked is tractable, as shown in this recent paper. Now, in this construction, it was important, although I whizzed past it too much to give a full explanation, that the two-sided ADS Schwarzschild black hole, or ADS flat Schwarzschild black hole, has an equilibrium state, the thermofield double state. Well, I use it in defining the trace, so it, I guess, was clear that we needed it. In important examples such as the Kerr black hole, or Kerr-Neumann black hole, or an ADS, or de Sitter Schwarzschild spacetime, there's no equilibrium state, so the discussion as presented doesn't apply. However, by starting instead from the Unruh state and operators on the past horizon, you can make a somewhat similar construction of a type 2 infinity algebra for those other spacetimes. And there are extensions to cosmology that I won't have time for, I'm afraid. How much time do I have? What's that? Okay, well, I'll be very quick in finishing. So this has an analog for de Sitter space that I actually think is more interesting, but I guess I don't have time for, because de Sitter space is less understood than a black hole. So here, see, for ADS, for the black hole, we actually could be looking at it from outside the universe. But in de Sitter space, it's a closed universe, so we have to look at it from inside. And therefore, we really have to consider the perspective of the observer and the observables that can be measured along the observer's world line. Unfortunately, I promised one of the panelists to say at least a word or two, but there isn't really time for it. In ordinary quantum field theory, we would again have a type 3 algebra for the green patch. And since it's a closed universe, the operator I called H would be a constraint operator. That means that only H invariant operators are allowed, so naively we should take the type 3 algebra A0, replace it by its H invariant subalgebra A0H. That doesn't work. A basic result in ergodic theory says that only C numbers commute with H. To get a sensible answer, we have to take seriously the fact that the reason we're interested in the static patch P is that there's an observer there. We need a model of the observer. The simplest model is that the observer has a rest mass plus a Hamiltonian of the observer's apparatus. We'll assume that if for M to be the mass, observer's rest mass, Q is bounded below by 0, but otherwise we give Q a continuous non-degenerate spectrum. So the Hilbert space of the observer is L2 of Q, where Q is non-negative. For the moment, we ignore the constraints and use the canonical conjugate P. I'm really going to finish as quickly as I can, but want to make it possible for Chris to continue as he's intending. So the naive algebra, including the observer, is obtained by adjoining both Q and P to A1. But then we have to impose the constraints. And the constraint generator now includes the H of the space-time plus the H of the observer. And now there is an interesting answer for the algebra of observables along the world line. And it can be described quite explicitly. It's generated by conjugated versions of the ordinary operators A, which you can think of as operators addressed to the world line, plus one more operator Q. And by conjugating by e to the minus IPH, you can show that this is, again, the cross-product algebra as defined earlier of type 2 infinity, but the constraint tells us that we should include a projection operator into states where Q is non-negative, and then the algebra we want with the projection operator before and after turns out to be of type 2-1. So that's a type 2-1 algebra appropriate to an observer in de Sitter space, and because it is of type 2-1, there's a maximum possible entropy. The state of maximum entropy is the maximally mixed state with density matrix 1. Concretely, it's empty de Sitter space now with the observer in equilibrium at the de Sitter temperature. So as was guessed, this justifies what was guessed long ago in purely thermodynamic grounds with no microscopic notion of entropy, that empty de Sitter space is a state of maximum entropy. So thank you for your attention, and my apologies for going over.
Okay, let's take a couple of quick questions so we can move on to the panelists quickly. Eva.
So thanks for the great review. It's everything we hoped it would be. I want to make a comment / question, which is, as you said, this global de Sitter space has no time-like boundary, and you've built in an observer that lives within that space-time. However, it does not follow from the positive cosmological constant that there is no time-like boundary in de Sitter. You can consider the possibility of a time-like boundary with positive cosmological constant. When you do that, the Hamiltonian is not constrained to 0. You have a notion of an energy spectrum, and many of the features of the space become more similar to the ADS CFT case. This will be explored later in the week on, I think, Thursday morning in talks of Aninos and Toroba. But I think it does fit into this session as well. So, yeah, if you have any comments on that, they'd be welcome.
Oh, I only will make a brief comment, which is that if you wanted to think of the observer as having a non-zero thickness, I modeled the observer as a geodesic. But if you want to think of planet Earth as the observer, all of us here on planet Earth, then planet Earth sweeps out a tube in space-time, and the surface of planet Earth could be your time-like boundary. So in the case that your time-like boundary is small compared to the de Sitter horizon, you could think of it, the time-like boundary itself, as being the observer in my discussion. And
I
then
agree.
you could equip if you have more in the model where the observer is seen as planet Earth, of course, my model of the observer was rather crude.
Well, I agree. There's some pretty good analogies between the two, but I think they're mathematically distinct. Either there's a notion of energy or there isn't. And if you have a time-like boundary with a well-defined boundary condition, for example, Dirichlet is actually well-defined in this case of a small spherical boundary, then you have a notion of energy which is, it really is distinct from planet Earth, which has a mass.
Well, in my presentation, the energy of the observer was mc squared plus q, which was a well-defined element in the algebra. So there was a well-defined notion of energy for the observer.
Okay, they're closely connected. I would love to discuss this further.
Okay.
Okay, I propose that, okay, maybe Lenny wants to ask a quick question.
I'm not sure if this is a question or a comment or a complaint, but no real observer can last forever.
Yes.
They'll eventually either evaporate into the horizon
Yes.
or fall into the horizon. So if I take a state with an observer and I assume that that observer is described by the same physics as everything else, it'll last a finite amount of time. In fact, if you run it backward, it'll also fall into the horizon. So the only conclusion would be that an observer is a fluctuation, a fluctuation which occurred in the thermal state, which occurs extremely rarely. If you ask how likely it is that such a thing can happen, it's incredibly exponentially small. And so it means that the amount of time that an observer is present in de Sitter space, I'm assuming eternal de Sitter space.
Yes.
That amount of time is negligible, very, very tiny. Don't we have to be able to describe all the rest of time in which there's no observer there? And if so, how do you do that?
Well, first of all, I certainly agree with you that an eternal observer is an idealization. I think what's really required is an observer with a lifetime long compared to the de Sitter, the cosmological timescale,
Okay,
which is
it
realistic.
depends on what your focus is. If my
Yeah,
focus is a really global description of the eternal time,
Yes.
then
No.
then we're going to be forced to some kind of theory which describes some kind of system
Yes.
in which fluctuations can happen, observers can come and go, and then we can ask conditional questions. What's the probability of such and such given that there's an observer
Yes.
there?
Well, certainly what I have described would be described more fundamentally along the lines that you say.
Yeah, yeah. We've talked about this a lot in the past. But it does suggest that some kind of theory which is independent of the existence of the observer ought to exist and be capable of describing the fluctuations in which an observer comes and goes and spends a tiny, tiny fraction of the time existing.
Perhaps. That would be nice.
Okay, I propose we move on. So let's move to the, let's thank Edward again.